we have the graph of y is equal to g of x right over here. And what I want to do is I want to check which of these statements are actually true and then check them off. And like always, I encourage you to pause the video and see if you could work through this on your own. So let's look at this first statement. So this first statement says both the limit of g of x as x approaches 6 from the right-hand side and the limit as x approaches 6 from the left-hand side of g of x exist. All right, so let's first think about the limit of g of x as x approaches 6 from the right-hand side, as we approach 6 from values greater than 6. So if we look over here, we could say, okay, when x is equal to 9, g of 9 is right over there, g of 8 is right over here, g of 7 is right over here. It looks like it's between -3 and -4. G of 6.5 looks like it's a little bit, it's still between -3 and -4, but it's closer to -3. G of 6.1 is even closer to -3. G of 6.01 is even closer to -3. So it looks like the limit from the right-hand side does exist. So it looks like this one exists. Now let's see, and I'm just looking at it graphically, and that's all they can expect you to do in an exercise like this. Now let's think about the limit as x approaches 6 from the left-hand side. So I could start anywhere, but let's say when x is equal to 3, g of 3 is a little more than 1. G of 4 looks like it's a little bit less than 2. G of 5 looks like it's close to 3. G of 5.5 looks like it's between 5 and 6. G of 5.75 looks like it's approaching 9. And as we get closer and closer, as x gets closer and closer to 6 from below, from values to the left of 6, it looks like we're unbounded. We are approaching infinity. And so technically we would say this limit does not exist. So this one does not exist. So I won't check this one off. Some people will say the limit is approaching infinity, but that technically is, infinity is not a value that you can say it is approaching in the classical formal definition of a limit. So for these purposes, we would just say this does not exist. Now let's see. They say the limit as x approaches 6 of g of x exists. Well, the only way that the limit exists is if both the left and the right limits exist and they approach the same thing. Well, we don't even, our limit as x approaches 6 from the negative side, or from the left-hand side, I guess I could say, does not even exist. So this cannot be true. So that's not going to be true. The first one's not going to be true. G is defined at x equals 6. So at x equals 6, it doesn't look like g is defined. Looking at this graph, I can't tell you what g of 6 should be. We have an open circle over here, so g of 6 is not equal to -3, and this goes up to infinity, and we have a vertical asymptote actually drawn right over here at x equals 6. So g is not defined at x equals 6, so I'll rule that one out. G is continuous at x equals 6. Well, you can see that it goes up to infinity, then it jumps down, back down here, then continues. So just when you just think about it in common sense language, it looks very discontinuous. And if you want to think about it more formally, in order for something to be continuous, the limit needs to exist at that value. The function needs to be defined at that value, and the value of the function needs to be equal to the value of the limit. And neither of these, the first two conditions aren't true, and so these can't even equal each other because neither of these exist. So this is not continuous at x equals 6, and so the only thing I could check here is none of the above. Let's do another one of these. So the first statement, both the right hand and the left hand limit exist as x approaches 3. So let's think about it. So x equals 3 is where we have this little discontinuity here, this jump discontinuity. So let's go from the positive, from values larger than 3. So when x is equal to 5, g of 5 is a little bit more negative than -3. G of 4 is between -2 and -3. G of 3.5 is getting a bit closer to -2. G of 3.1, it's getting even closer to -2. G of 3.01 is even closer to -2. So it looks like this limit right over here Oh, I'm circling the wrong one. It looks like this limit exists, and in fact, it looks like it is approaching -2. So this right over here is equal to -2. The limit of g of x as x approaches 3 from the right-hand side. And I'll think about it from the left-hand side. So we can start. I can start here. G of 1 looks like it's a little bit greater than -1. G of 2, it's less than 1. G of 2.5 is between 1 and 2. G of 2.9 looks like it's a little bit less than 2. G of 2.99 is getting even closer to 2. G of 2.999999 would be even closer to 2. So it looks like this thing right over here is approaching 2. So both of these limits, the limit from the right and the limit from the left, exist. The limit of g of x as x approaches 3 exists. So these are the one-sided limit. This is the actual limit. Now, in order for this to exist, both the right and left-handed limits need to exist, and they need to approach the same value. Well, this first statement, we saw that both of these exist, but they aren't approaching the same value. From the left, from the right, we are approaching -2, and from the left, we are approaching 2. So this limit does not exist. So I will not check that out, or I will not check that box. G is defined at x equals 3. Well, when x equals 3, we see a solid dot right over there. And so it is indeed defined. It is indeed defined there. G is continuous at x equals 3. Well, in order for G to be continuous at x equals 3, the limit must exist there. It must be defined there. And the value of the function there needs to be equal to the value of the limit. Well, the function is defined there, but the limit doesn't exist there. So it cannot be continuous. It cannot be continuous there. So I would cross that out. And I wouldn't click none of the above because I've already checked something, right? Or I've actually checked 2 things already.